The objective of this lecture is to provide an introduction to the two-body problem in spacecraft dynamics, to formulate the differential equation of motion associated with the two-body problem, and then to derive a solution of this differential equation. So we're going to start with the two-body problem. Now, this problem is set up as follows. Consider a system that consists of a spacecraft of mass m and a planet of mass big M. So furthermore, assume that both the spacecraft and the planet are in motion relative to an inertial reference frame which will be denoted I. So here's what the picture looks like. We have an inertial frame, which I will denote I. And for completeness, we have a point O, and O is fixed in I. And it's the point from which we are going to measure all our distances. We have a spacecraft and a planet. So first I'll draw the planet. The position of the planet is denoted, here's the planet, it has mass m. The position of the planet will be denoted R big M. We also have a spacecraft. The spacecraft has a position which I will call R little m, and the spacecraft is located as shown. The position of the spacecraft relative to the planet is the vector that takes me from the planet to the spacecraft, and that's R little m relative to big M, which for convenience will just be defined as R. Now, the goal is to be able to determine an equation that describes the motion of the spacecraft relative to the planet. That's the first part. So we're going to start as follows. We have to define a few things. We're going to say let Vmi be the inertial velocity of the spacecraft. And what I mean by the inertial velocity in this case is because I is the inertial frame. It's the velocity of the spacecraft as viewed by an observer fixed in I. The acceleration of the spacecraft, or the inertial acceleration of the spacecraft, will be denoted AMI. That's the inertial acceleration of the spacecraft. And then we similarly have two quantities that will be defined for the planet. The velocity of the planet as viewed by an observer fixed in the inertial frame will be compactly called the inertial velocity of the planet. And then the acceleration of m and I will be denoted the inertial acceleration of the planet. Now, given this terminology for completeness with the description, the velocity of m in I is equal to the rate of change in I of the position of m, and the acceleration of m, little m in I, which is the acceleration of the spacecraft, is the rate of change in I of the velocity of the spacecraft in reference frame I. And similarly, the velocity of the planet in I is equal to the rate of change in I of the position of the planet, and the acceleration of the planet in I is equal to the rate of change in I of the velocity of the planet in I. And all distances are measured from point O, where O is fixed in the inertial frame I. So that's our starting point. Now, we're going to take the next step in that it is assumed that the only force acting on either the spacecraft or the planet is that of gravitational attraction applied by the other body or applied by the other object. Now, what that means is that the only force that's being applied to the spacecraft is that of gravitational attraction applied by the planet, and vice versa. The only force applied to the planet is that of gravitational attraction applied by the spacecraft. So then, from that assumption, we can actually apply Newton's second law to both the spacecraft and the planet. So if we apply Newton's second law to the spacecraft, what we wind up with is that the force applied to the spacecraft is equal to the mass of the spacecraft times the inertial acceleration of the spacecraft. But because the assumption is that the only force that's being applied to the spacecraft is that of gravitational attraction due to the planet, we know that Fm, which is the force applied to the spacecraft, is equal to minus g times the product of the two masses divided by r cubed times r. And that comes from the diagram that we see back here, which is that the force applied to the spacecraft is due to the gravitational attraction of the planet, and it has to be in the direction opposite what I defined to be r, because that's the definition from the model that's taken, which is Newton's universal law of gravitation. So as a result of this, what we wind up with is we wind up with minus g times the product of the two masses divided by r cubed times r is equal to the mass of the spacecraft times the acceleration of the spacecraft. Now that's only for the spacecraft. Now we're going to do the same thing for the planet. So apply Newton's second law to the planet. Now in this particular case, the force applied to the planet is equal to the mass of the planet times the inertial acceleration of the planet. But from Newton's third law, the force applied to the planet is equal to the negative of the force applied to the spacecraft, because they have to be equal and opposite one another. So that has to equal g times the product of the two masses all divided by r cubed times r. And then that has to equal the mass of the planet times the inertial acceleration of the planet. So we now have two equations that we can put next to each other, which is that minus g times the product of the two masses divided by r cubed times r is equal to the mass of the spacecraft times the acceleration of the spacecraft. And we have g times the product of the two masses times the position, the relative position, the position of the spacecraft relative to the planet is equal to the mass of the planet times the acceleration of the planet. Now what we can do to be able to get this in terms of relative motion of the spacecraft, the motion of the spacecraft relative to the planet, is we can divide each equation by the respective masses. In the first case we divide by little m, in the second case we divide by big M, and then subtract. So if we first divide by each of the masses in each of these two equations, we get minus g times the mass of the planet divided by r cubed times r is equal to the acceleration of the spacecraft in the inertial frame. Similarly, if we do that for the second equation, we divide by the mass of the planet, we get g times the mass of the spacecraft all divided by r cubed times r is equal to the acceleration of the planet. Now let's subtract these two equations. And what we get is we get the acceleration of the spacecraft minus the acceleration of the planet is equal to minus g times the mass of the planet plus the mass of the spacecraft all divided by r cubed times r. But note that the acceleration of the spacecraft minus the acceleration of the planet in the inertial frame is what we can call AI. This is similar to what we called R. We have the same thing. We have AI, which is the acceleration of the spacecraft relative to the planet. So I can just abbreviate it as A. So as a result of that, we get that the acceleration of the spacecraft relative to the planet is equal to minus g times big M plus little m all divided by r cubed times r. Now let's take the next step here. This is a really important assumption, and it's actually a big part of how the two-body problem is formulated in spacecraft dynamics, which is that we assume, so this is a big assumption, is that the mass of the planet is much, much bigger than the mass of the spacecraft. And of course, that's a reasonable assumption because, generally speaking, planets are enormous in mass relative to any spacecraft. So as a result, that actually becomes a very good approximation. And as a result of that approximation, we wind up with the sum of these two masses is just equal to approximately the mass of the planet, from which we can actually simplify the equation further and get that the acceleration of the spacecraft relative to the planet is equal to minus g times the mass of the planet all divided by r cubed times r. Now for convenience, this is purely a convenience thing, but it actually turns out to be extremely useful in spaceflight mechanics. We make the following substitution. We say let mu equal g times m. This quantity mu is what's called the gravitational parameter. And of course, it depends on the planet, so it's called the gravitational parameter of the planet. So if we use mu instead of g times m, we get that the acceleration in I plus mu, well, take two steps here, is equal to minus mu over r cubed times r, which then tells us that the acceleration in I plus mu over r cubed times r is equal to 0. This last equation is what's called the two-body differential equation. Now, there's another thing about this equation that's actually comes from this assumption that the mass of the planet is much, much bigger than the spacecraft. If m is much, much bigger than m, then the position, or I could just say just the planet itself, the planet can be approximated to be an inertially fixed point. That's only true if the planet is much, much larger than the spacecraft in mass. If the planet's not much larger in mass than the spacecraft, then that assumption is not a good assumption. So as a result, what that tells me is that the acceleration in I, which is, remember, that's the acceleration of the spacecraft relative to the planet, because the planet now is going to be considered an inertially fixed point. This becomes the inertial acceleration of the spacecraft. So we now have yet another simplification that comes out of that assumption, which is that this becomes the inertial acceleration of the spacecraft. So now this equation doesn't just give us relative motion, but it gives us motion relative to an inertial frame under all these assumptions. So under the assumptions given or stated, the two-body differential equation provides a description of the motion of a spacecraft relative to an inertial reference frame. So that's actually somewhat useful because we've approximated the planet as being an inertially fixed point. So now let's go back to this equation for a minute. We have AI plus mu over r cubed times r is equal to 0. And remember, what that means also is because the acceleration is the inertial acceleration of the spacecraft, and that means that r, which is the position of the spacecraft relative to the planet, that position's being measured relative to an inertially fixed point. So everything in here winds up becoming measured relative to an inertially fixed point. So the goal now of the rest of this discussion, is to determine a solution. So this is what we want. We want a solution to the two-body differential equation. Now, one of the problems that arises in spacecraft dynamics is that this differential equation cannot actually be solved as a function of time. So the two-body differential equation cannot be solved as a function of time. The limitation is it can only be solved as a function of the location on the solution. Now that seems kind of a strange thing to say, but what that means is basically that we can figure out, if we know the location is going to be parameterized ultimately in terms of an angle. we can actually figure out what the radius is as a function of that angle, but we cannot figure out what that radius is as a function of time. And we're going to go through this in pieces here to be able to identify how to go about solving this differential equation. But in order to be able to do that, we first have to define a few key quantities. And these are properties of the two-body differential equation, which come in very handy and become very important quantities in spacecraft dynamics themselves. So the first of these is what's called the specific angular momentum. This actually becomes the most fundamental quantity in spacecraft dynamics, because once you have it, you can do a lot of other things which make it possible not only to solve this differential equation, but to be able to do a number of things downstream in terms of analysis. So we define the following quantity. We say let HI equal R crossed with VI. Now recall that R is the position of the spacecraft relative to the planet, but the planet is an inertially fixed point, so this becomes the position measured relative to an inertially fixed point. And similarly, the velocity becomes the velocity of the spacecraft as viewed by an observer fixed in the inertial frame. This is what's called specific angular momentum. And it's the specific angular momentum because it's divided by mass. Notice there's no mass in that equation. So the first thing we're going to do is we're going to notice something about this specific angular momentum. If we take the rate of change in I of the specific angular momentum, that's equal to the rate of change in I of R crossed with VI. But the rate of change of R crossed with VI in the inertial frame is equal to VI crossed with VI plus R crossed with AI, because I have to apply the product rule of differentiation, which is equal to, well, VI crossed with VI is 0, and then I get plus R crossed with AI. But from the two-body differential equation, AI is equal to minus mu over R cubed times R, and that in turn, because minus mu over R cubed is a scalar, gives me minus mu over R cubed times R crossed with R, but R crossed with R is 0, so this gives me the 0 vector. So as a result, it tells me that the rate of change in the inertial frame of the specific angular momentum is equal to 0. But if the rate of change of a vector in the inertial frame is 0, then that means that vector itself has to be fixed in the inertial frame. And that's a key property. H is fixed in the inertial frame. So now what we can do is we have this more information that actually comes out of the fact that H is fixed in the inertial frame. So let's go back to our picture. So here's the inertial frame. Now remember, at this point, the planet is now an inertially fixed point. So this is O, and this is actually the planet. So O is fixed in I, and it's actually the planet because we approximated the planet as being an inertially fixed point, and this is the inertial frame. And we have this vector, which I will point this vector in this direction. That vector is my specific angular momentum. And this vector is fixed in I. Now, as a result of it being fixed in I, let's think for a second. If a vector is fixed in I, then that means that that vector, since it's an inertially fixed direction, there's a plane that must be such that that vector is orthogonal to that plane. So I'm going to draw that plane. This is sort of just a schematic here, but there's a plane. Now, there's a plane that must be orthogonal to that vector, and this plane must also be fixed in the inertial frame because the vector itself is fixed in the inertial frame. And once you've defined a vector, there's always a plane that's orthogonal to that vector. Now, this vector, HI, is comprised of R and V, right? So HI, let's write this on the side here, is equal to R crossed with VI. It's the vector product of R with VI. So as a result of it being that vector product, we can draw R and V in this picture. Suppose that's R schematically, and suppose that this direction is VI. Because H is the vector product of R with VI, R and VI have to lie in this plane, which is orthogonal to H, because that's the definition of the vector product. The two vectors that are used to form the vector product are both orthogonal to the result of taking the vector product, and those two vectors form a plane. So this plane is not just any plane, but it's the plane containing R and VI. And of course, the plane that contains R and VI is the plane in which the solution lies, because the solution of this problem is to compute R. So that is equivalently what I call the plane of the solution to the two-body differential equation. So we have some more information here, which is that the plane in which the solution to the two-body differential equation lies is fixed in the inertial frame I. So we have an inertially fixed plane in which the solution lies. So in order to be able to now use that information, we need to somehow construct a direction in that plane, which is fixed in the inertial frame, that will allow us to be able to describe where the spacecraft is at any point in time. And we're actually going to do that now in the next step. We're going to use this angular momentum, the fact that it's fixed in the inertial frame, which means its rate of change in the inertial frame is 0, and the fact that there's a plane such that that vector h is normal to this plane, which is also fixed in the inertial frame and contains the solution to the two-body differential equation. All of that information is now going to be used to construct a direction that lies in that solution plane, and we're going to use that information to be able to then solve the two-body differential equation. So the first thing we're going to do is as follows, is recall the two-body differential equation itself. So in this particular case, the two-body differential equation, which we had from before, was as follows. We had AI plus mu over r cubed times r is equal to 0. That was the two-body differential equation. Now, to get started, we're going to actually, this doesn't look initially like it's going to do anything, but it's actually going to allow us to be able to integrate this differential equation once. So that's really the objective here. The objective here is first to try and find a way to integrate once. And we're going to get that by taking the following vector product. So take the vector product of the two-body differential equation with the specific angular momentum. So what happens when that operation is performed? AI plus mu over r cubed times r crossed with hi. Well, that still equals 0, of course, because I started off with something that's already 0. So this doesn't seem like it does anything. But it actually allows us to be able to do quite a bit. So the first thing we're going to do is we're going to split this up into two parts. I get ai crossed with hi plus mu over r cubed times r crossed with hi. And it's still equal to 0. Now let's look at each one of these terms. Let's look at the first term. Because hi is fixed in I, we can write the following, which is that ai crossed with hi is equal to the rate of change in the inertial frame of the inertial velocity crossed with hi. Now, how did I get that? Well, let's look on the right. If I take the rate of change in the inertial frame of vi crossed with hi, I get ai crossed with hi plus vi crossed with the rate of change in I of hi. But the rate of change of I in hi is the rate of change in the inertial frame of the specific angular momentum is 0 because the specific angular momentum is fixed in the inertial frame. So as a result of that, the rate of change of vi crossed with hi has to equal ai crossed with hi. So as you can see from this step, what I've been able to do is I've been able to write the first term after taking the cross product or the vector product with hi as the rate of change of something. So it would be useful now to be able to do the same thing with the second term. So the next objective is to write the second term, which in this case is mu over r cubed times r crossed with hi as the rate of change of some other quantity. So here's that's going to be done, how that's going to be done. So consider the following quantity. Which is, it's going to be mu times the rate of change in I of the position divided by the radius. Let's see if we can do something with this right here. Let's see what we can actually do to make this a little bit more tractable. So if we look at this, this is actually equal to mu times the rate of change in I of the inverse of the radius times the position. That's in turn equal to mu times, now we have to take a product. It's minus r to the minus 2 times r dot times the position plus r to the minus 1 times the inertial velocity. Or again, I just used the product rule for differentiation. But we have to notice something about this r dot because this is going to simplify tremendously once we can do that. So we note the following, that r squared is equal to r dotted with r dot. Sorry, r squared is equal to r dotted with r. Sorry, r dotted with r. Which implies that if I take the rate of change on both sides, I get 2r times r dot is equal to the rate of change of r dotted with r, which is r, stick with the same ordering, you get vi dotted with r plus r dotted with vi. The derivative of the first times the second plus the first times the derivative of the second, which is equal to 2r dotted with vi. So from this, you actually find that r dot is actually equal to r dotted with vi all divided by r. So that gives us a way to be able to, we can substitute that in now. So then we obtain that mu times d dt in I of the position divided by the radius is equal to, well, we wind up with mu times minus r to the minus 2, and then we have times r dot. But r dot is equal to r dotted with vi, all divided by r, the whole thing times the position, and then we have plus the inverse of the radius times the inertial velocity, which can be rewritten in the following way. We get mu times minus r dotted with vi, all divided by r cubed times r, and then we have plus vi, all divided by r. So that doesn't look like it does us a whole lot of good, but there's more simplification that can be done, which is that we can put this all over r cubed, and we get minus r dotted with vi, all divided by r cubed times r, plus r squared times vi, all divided by r cubed. So now what I'm going to do is I'm going to factor out the negative sign and the r cubed, which gives minus mu over r cubed times r dotted with vi, the whole thing multiplied by the position, minus r squared times vi, which can be further simplified or re-expressed, maybe a better way to put it, r dotted with vi times r minus r dotted with r times vi. Because again, r squared is equal to r dotted with r. So now what we can do is we can actually make another substitution here, which is that we can use what's called the vector triple product. So the vector triple product has the property that A crossed with B crossed with C is equal to A dotted with C times B minus A dotted with B times C. So if you apply the vector triple product to this expression that we have, so we apply the vector triple product, and we wind up with the following result, which is that mu times d dt in I of r, all divided by the radius, is then equal to, well, let's look at this. What do we get? We've got minus mu over r cubed times. Well, now we can start identifying things. We can see that r can be identified as what I called A, vi can be identified as what I called C, and then r again can be identified as B. So this becomes r crossed with r crossed with vi, which is equal to minus mu over the radius cubed times r crossed with hi. So this is a key property that we actually can use now to be able to substitute in to the expression that we had after we took the vector product of the two-body differential equation with the specific angular momentum. Namely, that we get that mu over r cubed times r crossed with hi is equal to minus mu times the rate of change in I of r divided by the radius. So now let's go all the way back to our substitution. When we actually said we were going to do all this, we had to figure out a way to be able to write the second term as a rate of change of something. Well, now we figured out how to write that thing as a rate of change of something. So what we wind up with is, we wind up with AI crossed with HI plus mu over r cubed times r crossed with HI is equal to d dt in I of vi crossed with hi, that's the first term, minus mu times d dt in I of the position divided by the radius. And that whole thing has to equal 0. But notice that mu is constant. So as a result, I can bring the rate of change out of the entire expression. So that winds up giving that d dt in I of this entire thing, we've got vi crossed with hi minus mu times r all divided by the radius is equal to 0. So now I have the rate of change of some quantity here, which is equal to 0, which means that the quantity that's in the square braces must be fixed in the inertial frame. So that implies that vi crossed with hi minus mu times r all divided by the radius is equal to, I should say equal, is fixed in the inertial frame. So what we're going to do is we're going to let C equal vi crossed with hi minus mu times r all divided by r. And this vector is actually what's called the Laplace vector. And the Laplace vector is fixed in the inertial frame I. Well, in other words, if you want it for completeness here, it says that dc dt in I is equal to 0. But we normally don't deal with the Laplace vector. We actually deal with everything scaled by the gravitational parameter. So we actually divide through by the gravitational parameter as follows, is that we say let E equal the Laplace vector divided by mu, which is equal to vi crossed with hi all divided by mu minus r all divided by the radius. And this vector is what's called the eccentricity vector. And of course, because the Laplace vector is fixed in I and the eccentricity vector is the Laplace vector scaled by a constant, the eccentricity vector is also fixed in I. E is fixed in I. So we now have a vector that's fixed in I that's not the specific angular momentum. So now we have two vectors that are fixed in I. So we have two vectors have now been found that are both fixed in the inertial reference frame I. So now we have to do something that actually is, well, what's useful about this second vector? So we observe the following quantity. So note, let's compute the following. Compute hi dotted with e. What do we get when we do that? hi dotted with e, which is also equal to e dotted with hi, is equal to vi crossed with hi all divided by mu minus r all divided by r dotted with hi. But that's equal to vi crossed with hi all divided by mu dotted with hi minus r all divided by r dotted with hi, which is equal to vi crossed with hi dotted with hi all divided by mu minus r dotted with hi all divided by r. Now let's look at the first term. vi crossed with hi must be orthogonal to hi. So the first term has to equal 0 because I'm taking the the scalar product of VI crossed with HI, and VI crossed with HI is orthogonal to HI, so that's 0. The second one is that R dotted with HI, that also has to equal 0 because HI is equal to R crossed with VI. So if I take one more step here and actually write this out, you get E dotted with HI is equal to, well, we've got VI crossed with HI dotted with HI, all divided by mu, minus R dotted with R crossed with VI, all divided by R. So now it becomes a little bit clearer that the first term is 0 because VI crossed with HI is orthogonal to HI, and it's just 0. And then we've got minus the second term. Well, R crossed with V is orthogonal to R, so that also gives me 0, which gives me a total of 0, which tells me that E is orthogonal to HI. So that tells me that E must lie in the plane of the solution. Or in other words, it must lie in the plane in which the solution to the two-body differential equation lies because it's orthogonal to H, and H is normal to that plane, as we already got through saying. So now, if I add to this picture, we can make the picture a little bit more complete, which is that I have this inertial frame, I have this plane, so I is the inertial frame. I have this point O, which is where the planet is. I have this vector H, which is normal to that plane. And then I have the plane itself. Now the plane itself is one in which this vector E lies. So E lies in this plane, as does R and VI. So E, R, and VI all lie in the plane of the solution. This is the plane in which the solution lies. So now we have some information that will allow us to be able to solve the two-body differential equation spatially. And here's how we're going to do that. Let's look down on this plane. So here's that plane that we had put at an angle before, but we're no longer going to put it at an angle. Here's point O. There's the direction of the eccentricity. There's the direction of the position. And I'm going to call the angle between these, I'm going to call it nu. Nu. So nu is the angle between E and R. It's the angle between the eccentricity vector and the position. Now, look what we can do with this. We can actually do something which is pretty interesting. If I take the scalar product of E with R, I get the magnitude of E times the magnitude of R times the cosine of the angle between them, which is nu. So suppose that we let E equal the magnitude of E, the eccentricity vector. This is what's actually called the eccentricity. It's a scalar, it's the eccentricity. Now we already have that R, the magnitude of R, is equal to just R itself. So this gives that E dotted with R is equal to ER times the cosine of nu. So that's one expression for E dotted with R. But we can get another expression. So another expression for E dotted with R can be obtained by using the expression for E itself. Expression obtained for E. And here's how we can do that. We get E dotted with R is equal to VI crossed with HI all divided by mu minus R all divided by R, the whole thing dotted with R. This is the second expression for E dotted with R. So let's break this up into pieces. And if we do that, we get VI crossed with HI, the whole thing dotted with R, all divided by mu, minus R dotted with R, all divided by R. But the second term here is just equal to R dotted with R is just R squared. So this gives VI crossed with HI dotted with R all divided by mu minus R squared all divided by R, which is equal to VI crossed with HI dotted with R all divided by mu minus R. So now let's look at this first term, which has a scalar triple product. So the scalar triple product has the form A dotted with B cross C. But that actually turns out to be equal to C dotted with A cross B. That's one of the identities. So we can actually use that fact on that first term here, which is that VI crossed with HI dotted with R is equal to R dotted with VI crossed with HI, where all I've done is just reversed the two factors because I'm dealing with a dot product. But that is equal to HI dotted with R crossed with VI. Now, R crossed with VI is just HI. So this is equal to HI dotted with HI, which I can call as H squared, where H is equal to the magnitude of HI. Now note something. Note that because HI is fixed in I, the magnitude of HI, which is equal to H, is a constant. Has to be, because otherwise the vector can't be fixed in a frame unless its magnitude is constant. If it's fixed in any frame and it's not zero, then its magnitude is some non-zero constant. So as a result of that, we can actually substitute that into this expression for E dotted with R. So E dotted with R then becomes, well, I've got VI crossed with HI dotted with R, which is just equal to H squared. So I get H squared over mu minus R. But note something, that this has to equal the first expression for E dotted with R, which is equal to ER times the cosine of nu. So I can now rearrange this further. I get H squared over mu is equal to, well, if I put this together, I get 1 plus E times the cosine of nu times R, which then I can solve for R, which gives R is equal to H squared over mu over 1 plus E times the cosine of nu. And this last result is what's called the orbit equation. Now the orbit equation actually, we'll get into more details on this a little bit later, but the orbit equation actually defines what's called a conic section, and that conic section is actually dependent on or the type of the conic section is actually dependent upon the value of E. And we will get into that in later on after we finish this lecture, when we get into more details on the values of E, etc. But we'll finish this lecture with one last little fact, which is the quantity h squared over mu is generally replaced with the following. P is equal to h squared over mu. P is what's called the semi-lattice rectum. And in terms of P, we get that R is equal to P over 1 plus E cosine of nu. So this is the original form of the orbit equation. And then this is the one that is obtained after the substitution in terms of the quantity P. So this is the orbit equation, written again just in terms of P. So to summarize this video, we started with the physical problem of a spacecraft moving relative to a planet. We determined the motion of the spacecraft relative to the planet, or I should say we determined the equation that describes the motion of the spacecraft relative to the planet. We then assumed that the planet was much, much larger in mass than the spacecraft, and as a result we could approximate the location of the planet as being an inertially fixed point, which gave us a differential equation that gave the motion of the spacecraft relative to an inertial reference frame rather than relative to a non-inertially fixed point, as the planet is now inertially fixed because of the assumption that the planet is much more massive than the spacecraft. From that, we actually defined a key property of the two-body differential equation, which was this vector called the specific angular momentum. We showed that that vector was actually fixed in the inertial frame. We then used that to be able to state that the solution for the two-body differential equation must lie itself in an inertially fixed plane, such that that vector was normal to that inertially fixed plane. We then defined, or we derived, a vector which was called E, which we called the eccentricity vector, and we found that that vector was actually fixed in the inertial frame as well, and it was in the plane in which the solution to the two-body differential equation lies. Using all of that information, we were then able to determine the solution of the two-body differential equation by taking the scalar product of the position of the spacecraft with the eccentricity vector, and we have two expressions for that scalar product. One which comes from the definition of the scalar product, the other one which came from, which arose from the eccentricity vector itself that we had derived. We equated those two expressions, and we were able to simplify the result to be able to obtain what became what we call the orbit equation. And that is the end of this lecture, where we now have an equation that describes spatially, we can describe the radius at any point along the solution of this two-body differential equation as a function of this angle nu. And in later lectures, we'll actually get into what is nu. We'll get into the properties of the two-body differential equation. Right now, that's where we're going to stop this particular lecture.